Week 1, lesson 8. Okay, so for this one, again, just reading the directions, I'm supposed to draw each vector and find its length, also known as magnitude in vector speak. All right, so if I draw vector A, I need to pick some starting point. Again, doesn't matter. Go to the right 3 and up 1, 2, 3, 4. 1, 2, 3, 1, 2, 3, 4. Okay, so if I kind of look at that little right triangle right there with this as being a length of 3 and this being a length of 4, it makes perfect sense using Pythagorean theorem and the fact that you have this memorized as a Pythagorean triple that would be a 5. Okay, so this is again vector A. Next, let's talk about vector B, where I'm going to have to go left 5, 1, 2, 3, 4, 5, and down 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Ooh, that was a very close guess there. So here's vector B. And again, that's another Pythagorean triple. Maybe you have it memorized, maybe you don't, but that would be 13. If you wanted to see it, the Pythagorean theorem, it would be 25 plus 144, which is the square root of 169. All right, and then vector C, it looks like I'm going to the right 2, sorry, I shouldn't have drawn that little bit in. Right 2 and up 2, so we've got, no, I'm lying, it's not up 2, it's down 2. It's right 2 and down 2. That's vector C. The length of it, if this is 2 and that's 2, hypotenuse squared would be 4 plus 4. Hypotenuse squared is 8. Square root of 8, which is 2 rad 2. All right, so looking down here, you can see the formulas for magnitudes of vectors. It should look a whole lot like the Pythagorean theorem, or even more importantly, it should look like the distance formula, right? This is the distance formula in 2 dimensions, but some of these vectors that we're going to be dealing with might be in 3 dimensions, so there's an extra part over here for the third coordinate. Scooting this up. Okay, so a unit vector, by definition, is in the same direction as a given vector, but it only has a magnitude of 1. Okay, so if I graph vector D and it's 5i, that would be 1, 2, 3, 4, 5. That would be vector D. But if I want a unit vector, and here's some cool notation, it wears a little hat, right? That's a unit vector in the direction of D. It would have to just be I, right? This would be a unit vector in the same direction. Now, all you have to do is if you know the magnitude of the original, right, and the magnitude of D is 5, then you just divide the original vector by the magnitude and you'll get the unit vector. So let's try one that's not quite so easy, right? It's not bad, but just kind of using this. So let's find a unit vector in this direction. In order to do that, I need to know what the magnitude of V is. So using the formula, I'm going to take the X direction component and square it, and the Y direction component and square it. That's the square root of 25 plus 144. Oh, hey, didn't I just write this a couple seconds ago? Isn't that magnitude 13? So if I want a unit vector, there's my notation. I'm just going to take the original vector and divide by 13. Okay, let's try another one. One in 3 dimensions. All right, so the magnitude of C is going to be the X direction and the Y direction and the Z direction all squared. So this is 9 plus 16 plus 25, which is the square root of 50, which is 5 rad 2. Okay, so again, unit vector has to wear the little hat, right? Notation's important. And I just have to take the original vector and divide it, right? Take the original vector and divide each term by the magnitude. All right, so now let's take a look at this example where they give me two vectors, and we want all the values of k, right? Because notice this vector doesn't have actual numbers in there. It has a variable, such that the magnitude of c is equal to twice the magnitude of d. All right, so let's figure out the magnitudes of each. Magnitude of c is just going to be 49 plus 36, or the square root of 85. D is going to be the square root of the first component squared plus the second component squared. So that's 5k squared, or k rad 5. Okay, so now that I've got, sorry, I forgot some notation. All right, since I've got these magnitudes, let me plug into this and see what I can do about solving for k. So I've got, let's see, rad 85 equal to 2 times k rad 5. All right, so let's see. I'm thinking that to get rid of those square roots on both sides, let me just square both sides of this equation. 85 equals 4k squared times 5. Simplifying for k squared, I have 85 over 20. Reducing that, I get 17 over 4. And lastly, taking the square root, I get plus or minus rad 17 all over 2. All right, parallel vectors are called scalar multiples of each other. Okay, so you just did an assignment on scalar multiples in Delta Math. So hopefully you remember that it's literally just multiplying a number times the vector. They have the exact same direction, but different magnitudes, right? So like this vector would be considered to be parallel to that vector, or this vector could be considered to be parallel to that vector, because they're pointed in the same direction, they just have different magnitudes. So to show, for this example, let me scoot this up. To show that these two vectors are parallel, I just have to show that one of them times a scalar could equal the other one. In other words, that's not what I wanted to write. Let's try that again. One of them times some sort of a scalar equals the other one. Whoa, that's a highlighter, not an eraser. There we go. I'm having issues, guys. There we go. All right, so that means I have 2k equals 10 along with 4k equals 20. And as long as those k's are the same, then they're parallel. It has the exact same scalar. All right, so last example, let's find a parallel vector. Okay, parallel means same direction. So I need to, oh, hold on. And it has to have a magnitude of 6. Okay, so let's figure out what its current magnitude is. Currently, let's see, that's 9 and 4 and 100. Currently, its magnitude is the square root of 113. Okay, but I want that instead to be 6. So can you see that if I took this and I multiplied it by 6 over rad 113, that the 113 under the radicals would cancel out, and I get a magnitude of 6. So this is what I need to multiply this entire vector by. Let me write the vector up. Right, there's the original. And I'm going to multiply each term by 6 over rad 113. 6 over rad 113. 6 over rad 113. And let's just kind of simplify that. So I end up with 18i over rad 113 minus 12j over rad 113 plus 60k over rad 113. That magnitude has the same direction, but a different magnitude.